Hey everybody, welcome to section 4.4, properties of definite integrals. We're going to get right into it today, and what I'm going to do is I'm going to give you the first property that they talk about is how we can add integrals together. Now, this won't seem very surprising to you. You probably expect this is going to happen, but suppose we've got some curve, and there's my function. We'll call that f of x, or the function f. And suppose I'm trying to integrate between a and b. So I'm trying to find the area under the curve between a and b. The addition property of integrals just says if I have a continuous function, which f of x is a continuous function, there's no gaps or holes or jumps or anything in there, and I have another value, say c, somewhere in between here. Now, it's probably not surprising to you that in order to get this whole integral, f of x dx, from a to b, if I put some value c in between there, I can do that by doing this first area from a to c of f of x dx, plus adding the second area from c to b of f of x dx. And it looks like it should be simple enough. And actually, that's all the property is. It looks kind of weird because we're not in alphabetical order now, but if c is any value between a and b and f of x is a continuous function, this property always holds. And so we're going to talk about some times where we would want to see this, where we're going to use this. All right, so I'm going to just jump right into a problem. This is problem 4 out of the book. And what they do, you may remember a problem like this from college algebra, where it's a piecewise defined function. So they give us the function g of x, and it's defined to be negative x squared plus 5 anytime x is less than or equal to 0. Let's move that up a little bit so I don't pull up anything accidentally. But it's also defined to be just x plus 5 for x greater than 0. Now, I'm going to draw the picture, although you don't need to draw the picture to do the problem, because what we're saying is if we're thinking about a number line, I should probably read you what the question says. Find the area under the graph over negative 2 to 3. Find area under the curve and then they give closed interval negative 2 to 3. And so you've probably already assumed we're just going to use the property we just used before. We're going to go from negative 2. Notice 0 is in this interval someplace. So what we're going to do is we're going to integrate from negative 2 to 0 of g of x dx plus, let me erase this to get it out of the way, and then we're going to integrate from 0 to 3 of g of x dx. So that's exactly what we're doing. They gave us a point. That was the 0 is the point c, essentially. And then we know from negative 2 to 0, oh, that's when x is less than or equal to 0. So what we're going to do, and I'll just write it all in there. So my total area is going to be negative 2 to 0. Now notice those x values are all between negative 2 and 0, so they're all less than or equal to 0. So for that, I'm going to go to the first one. So that's picking up this piece here on top. When x is less than or equal to 0, which it is, going from negative 2 to 0, I'm going to use negative x squared plus 5 dx. And then I'm going to add to that, starting at 0 and going all the way to 3, the end of our interval, the other piece. Because 0 to 3 is obviously greater than 0. So I'm going x plus 5. And we don't have to worry about 0 itself, because at 0 itself, that's just a line, has no area. So we don't have to worry about the inequality as far as the area goes. And I'll show that when I draw the picture. But for that piece, I'm just using the x plus 5. And then after I work this out, we'll show you the curve. There's going to be quite a bit of work going on here. So let's go ahead and do that, and I'll graph the curve. So I do the antiderivative. So remember, the exponent goes up by 1. So I've got negative x cubed, but I multiply by the reciprocal, plus 5x. And I'm going to evaluate that from -2 to 0. And then whatever I get there, I'm going to add to it x squared, right? That's x to the first, I go up 1, multiply by the reciprocal, plus 5x. And I'm going to evaluate that 0 to 3. The zeros are going to be real nice here. It's going to get rid of half of our work. So let's see, I plug in the 0. So I go -1/3 times 0 cubed plus 5 times 0. That's the first piece. Minus the second piece. Now I plug in the -2. -1/3 times -2 cubed plus 5 times -2. And that whole thing, that's my first piece. And then I go plus, and then I do the second one. And I do that similarly. So now I've got the 1/2 x squared, plug in the 3, plus 5 times 3, minus, and then I plug in the 0. 1/2 times 0 squared, plus 5 times 0. Remember, these are polynomials. This is the second piece. Remember, these are polynomials. So when I plug in 0, everything's got an x in it. So all that's going to disappear. Remember, that doesn't happen if I have an e to a power, because e to the 0, remember, is 1. So that doesn't just cancel out. But notice, this whole piece here is just going to be a 0. Because 1/2 times 0 squared, of course, is 0 plus 5 times 0. This piece here is also 0. So those I don't even have to worry about, which is why I said half the work. Okay, so now I've got this negative outside this bracket. And I'm going to do this kind of in my head a little bit. So I've got -2 cubed, which is -8, times -1/3. So it's +8/3. This one, notice, is -10. But since I have thirds, rather than doing my calculator, I'll just get everything to have a common denominator. I have halves over there. I'll have to go to 6. That's okay. We'll do it anyway. So I've got -10, but as thirds, it's -30 thirds. Okay, so that was just multiplying that by 3 over 3, of course. I don't want that big mark. So that was just times 3 over 3. That's where that came from. And again, if you don't want to get these as fractions, just plug them in your calculator. That's fine. So here I've got 2 squared, which is 9. So now I have 9 halves plus 15. Well, 15 is 30 halves. All right, so going on. So now I've got 8 minus 30, which is -22 thirds, but I've got this negative on the outside, so it's going to become positive, plus 39 halves. I don't need a bracket there. I'll keep it here for this last step. Now I'm going to get a common denominator again, so just bear with me. I'm going to multiply this by 3 over 3 and this by 2 over 2, just to get 6 as a common denominator. So let's see, the negatives will cancel out. I'll get 44/6 plus, let's see, 78/6. And then I can add those together. I've got 110, 122/6. Let's see, those add up to 5. 3 doesn't go in there, so it's not divisible by 3, but it is divisible by 2. So let's see, I get 61 over 3. So there's my answer, 61 thirds. Let's erase that bottom line, I didn't like it. Or if you wanted to change it to a mixed number, 3 goes in there 20 times with 1 left over. Or if you wanted to approximate it, so had you just plugged it into your calculator, you would have got 20.3 repeating. We'll just put a little line over the 3. I guess we don't need the approximate if I put the line over the 3. Well, here. So we won't put the line over the 3. We'll just go to one decimal place, and we get 20.3, approximately. Let's see. So that was in the book. That was problem 4. And they got a different answer than we did. That's not good. Son of a gun. Let's see if we can pick it up real quickly. So we had negative x squared plus 5. We had x plus 5. So that gives me negative 1/3 x cubed plus 5x, 1/2 x squared plus 5x. Those go to zeros. Negative 8, so 8/3 minus 10, so 30/3, that's minus 10. 9/2 and 15 is 30/2, 39/2. Did anybody see what I did? Negative 22/3, I didn't see what I did. 44/6, and oh, it was my 39 times 3, wasn't it? Good heavens. So I was good all the way to there. 39 times 3. It's just like class. So let's see. Let's erase what I did wrong. This is wrong. So all of this is wrong. Good thing we checked. You guys would be saying, Professor Mon, you have the wrong answer. I'd be like, oh yeah. So 39 times 3 is 117 plus 44, 161. And I'll just get a calculator approximation. 161 divided by 6, 26.83. So that's my approximate. If you want that as a fraction, I will convert it to a fraction for you. 161/6, which is what we had. And we can divide that by 6 if we wanted to. And if we do that, we get 26 5/6. So I'll just leave it as approximately 26.83 because that's what you'll get in your calculator. Now let me show you just real quickly what this graph is so we see what we actually found. So remember, it was the area under that curve. So it was negative x squared plus 5 when it's less than or equal to 1. Negative x squared plus 5. Remember that graph, negative x squared plus 5, it's a parabola, goes up through 5, goes down. But we only want that graph for x less than or equal to 0. So I'm only pulling this piece right here, because that's when x is less than or equal to 0. So essentially, I just erased the blue one, and that's gone. And then the other graph was just x plus 5. Well, x plus 5 is, we'll do something similar. X plus 5 is a line with a slope of 1, goes through 5. I don't know where that's going to go as far as that goes. X squared when y is 0. I get x squared is 5, square root of 5. Nah, it's over here. So the graph goes something like this, but I just want that when it's greater. So if I erase this piece, that's what my graph looks like. I lost my x-axis somewhere. So it's there. But I've got this little point right here, kind of a corner. It's not differentiable there. I can't take the derivative there. There's a little cusp. But what I did is I found the area, that 22/3 that I did before was the area under the curve here. And then when I got to 3, it's the area under the curve here. So I added those two areas up. Now, this point right here, we were going out to -2, but if I did negative x squared plus 5 equals 0, I get, well, let's say it this way. 5 equals x squared, x equals the square root of 5, which is a little over 2. And we went out to -2. It's plus or minus, of course. So that's a little past -2. We only went to 2, so we only went about this far. We didn't go quite all the way out there. But that's my graph. So there's from -2 to 3. That's what I found the area of. Not terribly exciting, but I couldn't do it all in one piece because that's not that graph has that little break right there. It's a different formula. The formula here is -x squared plus 5, but the formula here is just x plus 5. So I had two separate functions I had to plug in. So anyway, that was my graph. I had to do it piecewise, which is why they gave us this example, of course, right after they showed us that property. Okay, so that's the idea of that property. What I'm going to do is I'm going to jump up to another piece. There's actually another property that we're going to talk about. And it's talking about the area between two curves. Area between two curves. And so think about it. Let's say I have a curve here and maybe one curve looks like this. We've got another parabola, kind of a parabola. And maybe we've got another curve that's another parabola. Say it looks like this. And what I'm looking for is this area right in here. That's the area between those two curves. Well, let's call this curve F and this curve G. And this point of intersection we'll call A, and this point of intersection we'll call B. So think about how we're going to find that. Here's how we're going to find the area between those two curves. If I integrate from A to B, now if I do just f of x dx, think about what that's going to be. That's going to give me all this area under the black curve, because that's the curve F. I don't want all that area because I don't want this little area down here. I need to take that away. If I take that away, it's only going to leave me with the blue area, which is the area I want. Well, that blue area, okay, think that blue area is in the black, so that's what I wrote, the integral from A to B of f of x dx, but I want to take away that green area. Well, so what I want to take away is the integral from A to B of g of x dx, because that's the area under the blue curve, the G curve, which is that green area. And so if I have the black area, right, this was the black area, and I'm subtracting away the green area, notice that's only going to leave me with blue. Now, you probably never knew that black minus green was blue, but in this case, obviously it is. But so that's how we find the area between two curves, is this nice little formula right here. Notice this curve was the top curve, this one's the bottom curve. Because in that area, the top F was the top curve, and then G was the bottom curve. If I do bottom minus top accidentally, I'll get the correct area, but it'll be negative. Areas can't be negative, so I'd have to take the absolute value. So what we're going to do is we're just going to make sure our top area is always the first one that we do. So I've pulled out a problem to do that. It's problem 20 in my edition of the book. So let's do that. Again, we don't need to graph it, but if you want to do a quick sketch, you certainly could. I will graph it because I know what these look like. You may also. Y equals x squared minus 6x, and y equals negative x. So there's my two curves, and it says find area bounded by the two curves. All right, couple things here that we haven't seen. First of all, what I need to do is I need to find out what area is bounded by those two curves. So I need to find where those curves intersect. If I look at those curves, notice that first curve's a parabola that opens up. I don't know exactly where it is. I could fiddle with it. I don't care that much. I just know here, you know what? Let's do this. We'll get rid of the x and y axes. because I know that first curve is a parabola that opens up. I know the second curve is a line that goes down. So if they intersect, the line is the top curve, right? Because I'm looking at this area right here. And the parabola is the bottom curve. So this one's the bottom. This one's the top. And if you don't know what the curve looks like, it doesn't matter. I'll tell you how we're going to find out which one's the top or the bottom. First, we have to find out where they intersect. So those are the points of intersection. Points of intersection. Oops, I don't want that. And so to find the points of intersection, set equations equal. Because that's when they intersect, is when the two equations are equal to each other. So I come back up here and I go x squared minus 6x equals negative x, and I need to solve that. So I have to add x to both sides. What I'm doing is I'm getting it set equal to 0 so that I can factor it out. And I can factor out an x, and I get x minus 5. So I go, oh, either x equals 0 or x equals 5. Those are my limits of integration. So I'm going to integrate from 0 to 5. So when I do that, let's see, well, I forget this. So the negative x is on top. So I've got my integral from 0 to 5, negative x minus x squared minus 6x. This was the top, this was the bottom. We always do top minus bottom. If you end up getting a negative answer, it means one of two things: you did it wrong, or you did it backwards. All right, here's how we can tell which one's on top real easily. Let's see, I'll put it over here. Which curve is on top? You pick a value between 0 and 5. Pick any value. I'm going to say between A and B, because remember, we're integrating from A to B. And so in this case, 0 to 5. Plug into both equations. Biggest number is top. Biggest value is top equation. Because what we're doing is we're finding the y values when we plug it into the function. So here's what we're saying is, if I plug in, say in our case, x equals 1 is in between. So if I plug that into the first equation, y equals 1 squared minus 6 times 1. I get 1 minus 6 is negative 5. If I plug it into the other equation, y equals negative x, I get negative 1. Oh, negative 1 is bigger than negative 5, so that's the top. And that's what we said, the y negative x, which was what this equation was, is on top. The y equals x squared minus 6x was on the bottom. And you can just do that in your head. It wasn't real hard to do if you know what you're doing. Okay, otherwise you have to draw the curves. So anyway, I'm going to integrate this. I have 0 to 5, negative x minus x squared plus 6x dx, which is 0 to 5. Now the negative x and the 6x is just 5x minus x squared. Notice it's always what we had up here that we solved, that 5x minus x squared minus 5x. It's the opposite of that one, because opposite. All right. Anyway, now we're going to integrate. We've done all the work. The rest of this is stuff we already know how to do. So I'm going to go 5x squared, but times a half. Now, again, that's not 5.5, it's 5 times, minus x to the third, but 1/3. And I'm going to evaluate it from 0 to 5. So I'm going to call that 5 halves. We're going to plug in the 5. 5 halves x squared minus 1/3 times 5 cubed minus, then I plug in the 0. 5 halves times 0 squared minus 1/3 times 0 to the third. Notice again, this whole piece, the 0 squared times 5 halves is 0, minus 1/3 times 0 cubed is also 0. This whole thing is just 0. But do check, make sure it is. So I've got 5 squared is 25 times 5 is 125 halves minus 125 thirds. And rather than messing with that and getting a common denominator, I'm just going to plug it into my calculator. So I get 125 divided by 2 minus 125 divided by 3, and I get about 20.83. And that's my answer. Is that the same answer I got last time? 26.83. That was close. All right. So anyway, that's how you find the area between the curves. You have to find where the curves intersect. That's what you're going to integrate from. And then you just do one curve minus the other curve. It's an area, so the answer has to be positive. If you get a negative, you might want to just change it to a positive and say, oh, I must have subtracted the bottom one minus the top one. Okay. So that's where we are there. Let's see. Problem 28. We're not going to do 28. 28's kind of just like what we did there. So let's do the last idea that they give us is how to find the average value of a function. So let's look at this. Average value of a function. And you're not going to be shocked by this, I don't think. It looks a little weird, but it's not. Because think, anytime we want to find the average, we always do it the same way. We get the total and we divide it by whatever number we had. So if I wanted my average exam score, I'd add up all my exam scores, get the total exam score, and then divide it by the number of exams. And so that's the idea. So this, that number, whatever it is, here's what we do. Remember, in calculus, the way we find the total is we integrate. So we go, oh, from A to B, whatever my function is, with respect to x, that's going to give me my total. The number, well, think of what I'm doing. I've got some curve. I'm going from A to B. So there's my total. That's my integral piece. But to get the average, I have to divide by however long this is. Well, that's b minus a. That's that length. So this is b minus a. They don't write it that way because that looks weird. So what they do is they call it y average. And what we get is they kind of pull this out. Think of a 1 up here. They're going to pull that out as 1 over b minus a times the integral from a to b of f of x dx. And that's my average value function. So it's the same integral. We're essentially multiplying by the reciprocal of the distance or just dividing by the distance. Either way you want to see it. They write it that way. So we will as well. All right. So I have a problem like that, and then we'll do an application of that. So let's see. So let's do, we're just actually jumping into an application. So this is problem 48. Let me pull out 48 for you. So I've already got it. I've copied it so that we can read the problem. So let's do this. We'll go in, and the problem is here. Notice I only have one in here to copy and paste for you. So let's go there. We'll paste that in here. And here's our problem. Accumulated sales. Music Manager Limited estimates that monthly revenue R of T in thousands of dollars attributable to its website T months after the site was launched is given by R of T equals 0.5 e to the T. Find the average monthly revenue. So notice they're saying average monthly revenue attributable to the site for the first 4 months of sale. So what I'm going to do is I'm going to take the integral of revenue. Let's see. So I'm going to go the integral of R of T. Should I write that? Let's not even write that. So I'm going to go the integral of 0.5 e to the T with respect to T. In the first 4 months, I'm going to go 0 to 4. That's going to mean total. But again, I would divide by the 4 minus 0. But instead, we're just going to say, oh, it's 1 over 4 minus 0. So rather than having to write it as divided by and have this crazy looking fraction, we'll just write it this way. So essentially, it's just 1/4. And now I need to integrate. Well, the antiderivative, the constant multiple stays. The antiderivative e to the t is just e to the t. And I'm going to go from 0 to 4. Now, you may want to change that 0.5 to a 1/2. I probably would. But if not, we'll just leave it. We'll just plug it all into our calculator anyway. It's not going to be a big deal. So I'm going to go 0.5 e to the 4 minus 0.5 e to the 0. Now, here's where I was saying be careful, because that e to the 0 is equal to 1. That doesn't make this whole thing go to 0. So don't just say, oh, it's a 0 like in the other ones. It goes away. We can ignore it. We cannot ignore it. So I get that I'd like to ignore. So I get 1/4. I don't know why I'm writing this down. I'm just plug everything into my calculator. So let's do this. So on the calculator, I'm going to go 1 divided by 4. I'd probably just plug in 0.25. But I actually did 1 divided by 4. Parentheses, 0.5 e to the 4th. Close the parentheses for my 4th power, minus 0.5 e to the 0. I'm not going to close any of those parentheses. And I get, let's see how many decimals they want to go to. Remember, we're in thousands of dollars, so I'm going to end up having to move the decimal 3 places. I'm guessing, are they going to go to the nearest 1,000? They actually go to the nearest penny. So let's go. So we have I'm looking in the book and I'm saying that's not the answer, but that 47 in that book's not 47 in this book. It's actually 48. So I do have this number. So it's, let's see, on my calculator it says 6.699 and it's 768, so we'll round to 77. And that's a decimal right there, but they said it's in thousands of dollars. Up here, in thousands of dollars. So what I have to do is I have to take that and I have to multiply by 1,000, which moves the decimal 3 places. So now it's $6,699.77. Now, think what that is. That's not the total revenue. That's the average revenue per day for the first 4 days. I'm going to box that. Also, they didn't ask for that, but you know how I always like you to explain things on the test. I don't know if I'll have you explain it on the test because it's whatever it asks on the computer, but in class, I would ask you to explain that. Okay, So that's the idea. Those are the three big things that went on. Is we had how to find, well, let's see, what did we start with? How to add the integrals together, how to find the area between two curves, and then how to find the average value of a function. So 3 ideas in this section. Practice those up. There's problems in the book. You can look at those. We'll talk more about this in the live session, but that's what this section's all about. So again, 3 main ideas. We did an example of each. Definitely ask me if you have questions on those, but I think you'll be able to get it. So work on those, and we'll talk more about this when we meet next time. All right. Best of luck, and I will talk to you again soon.